Superconducting versus Semiconducting Electronic Ground State in Chirality-Specific Double-Wall Carbon Nanotubes. The authors of this paper, Dr. Ting Chang and Professor Ping Sheng, are from the Department of Physics, Hong Kong University of Science and Technology. After the discovery of superconductivity in carbon nanotube systems, theoretical analysis show in quasi-one-dimensional CNTs electron-phonon interaction can offer two potential ground states, superconductivity and Peierls distorted semiconducting state. Then, Coulomb interaction between electrons becomes the deciding factor, and screening of Coulomb interaction is crucial for the appearance of superconductivity in CNTs. The superconductivity behaviors usually occur in CNT bundles. A single-wall CNT is known to be semiconducting at zero temperature. An interesting question is, how about a single metallic double-wall carbon nanotube? Here, we consider two of them, the 3, in 8, and 5, in 15, respectively. The inner tubes are with strong electron-phonon interaction to provide possibilities of electron-phonon-related processes, and the outer tubes are metallic so as to provide screening of Coulomb interaction in the inner tube. Interaction between electrons can have two components. One is the attractive phonon-mediated coupling. The other is the repulsive Coulomb interaction. We estimate the magnitude of the first one from the density functional theory, and the second one is estimated with and without screening of the outer shell, for comparison. Then we perform second-order renormalization group analysis to identify the system behaviors in cooling process and the zero-temperature ground state. With a single CNT, the electric lines spread over all the space. This is the bare Coulomb coupling without screening. However, if there is an outer metallic shell, the Coulomb interaction will be screened, and its strength can be estimated with a random phase approximation. It is about 1 to 2 order of magnitude smaller than the bare potential. With renormalization group analysis, for single-wall 3, and 5, CNTs, we get Peierls distorted semiconducting ground state, in agreement with all the prior theoretical predictions. In the plots, moving from 0 to -infinity along x-axis represents the cooling process approaching zero temperature. The y-axis denotes the amplitude of different order parameters. Black lines denote charge density wave, and red lines denote singlet superconductivity. The charge density wave order is seen to diverge much faster than the superconducting order in both single-wall CNTs. When inner tubes are embedded in DW-CNTs, the results are quite different. In both systems, singlet superconductivity order exceeds charge density wave order in the cooling process, and this indicates at zero temperature, the ground state is superconducting. The crossover temperature of 3 at 8 DW-CNT is extremely low, while for 5, at 15, is relatively higher. This may be attributed to the difference in the electron-phonon coupling strength of the two systems. The screening due to outer tube greatly modifies the ground state. This is the main result of our paper. Screening due to the outer shell of DW-CNTs efficiently reduces Coulomb interaction between electrons. As a result, RG analysis shows two systems have superconducting ground state. The broad implication of our result is that most of the metallic DW-CNTs can become superconducting at low temperatures, in agreement with the experiment.